Hi there, this is Richard Walker from Lucidate. Welcome to this fifth video in Lucidate's series on AI and computer vision. The last video delved deeply into the maths behind neural networks, specifically the use of calculus and backpropagation to optimize the network's parameters. In this video, we'll first build a neural network and train it to identify images of clothes. We'll establish a design paradigm, use it, interpret it, improve it. We'll use this cycle to gain a better understanding of what our AI is doing and use that understanding to improve its performance. In this video, we'll introduce some tools that help us better visualize how the network is behaving. This will greatly improve our ability to tweak the performance of our AI. We'll start by quickly reviewing our computer vision challenge. We'll then introduce three visualization tools: the performance chart, the confusion matrix, and the prediction histogram. We'll apply these tools to our computer vision problem. Finally, we'll extend our scope to get our network to recognize other types of image. Our challenge is to get our AI to classify images of clothes. We've chosen to apply a neural network. This technique applies calculus rather than logic to spot patterns in input data. As we train our network, we present it with a series of images. We'll initially split these images into two unequal sets. The larger of the two sets will be used to train the network. The smaller set will be held back until the network has completed training. Once completed, we can then show the test images to the network. We'll score the performance of the network on how well it performs on the images that it has not seen. So far, we've discussed a lot of concepts, but we haven't spoken about implementation. How actually do we build, train, and run a neural network? This turns out to be very easy. Over the past decade, many firms have built strong AI capabilities. They have decided to open source their machine learning libraries. Alphabet Google has released TensorFlow, Meta Facebook has released PyTorch, and Microsoft has released CNTK. A popular AI interface called Keras has been built to easily access these libraries. This allows firms like Lucidate to create very simple GUIs to build, train, and test neural networks. I'm not fond of showing code on screen, but I hope you will allow me this time, as I'm doing it to show you how little code is required. And also, the code maps very closely to the way that we've been talking about neural networks. This code is Python, and this handful of lines is all that is required to build, train, and test a neural network using the Keras API. The first line of code is split over 4 lines on the screen, just to make it easy to see what's going on. Here we set up the layers of the network. An input layer, which flattens the 28 by 28 pixel intensities, 2 hidden layers of 128 and 64 neurons, and an output layer of 10 neurons. If we want more layers, we just add more lines of code like these. And if we want more neurons, we just tweak these variables. Here we also specify the activation function, in this case, ReLU. The next line is more complicated to look at, but all it's really doing is setting up the cost function, not as scary as it looks. We're on firmer ground with the next line. We get to choose how many epochs we will train for, and we get to say what the training inputs and outputs are. With our network trained, we can now see how well it performs on our test data and print out the results. Pretty straightforward. Thank you, Keras. Firms like Lucidate can then write applications with user interfaces that populate these functions. Here we can see a GUI to choose the dataset, specify the activation function, input the number of layers along with the corresponding neurons, then train and test the network before saving the results. When training, we calculate the cost function after each presented training sample. Neural networks are great at matching patterns, sometimes too good. If there's some implicit or explicit order in the data, there's a good chance that the network will find it. This is an example of overfitting. This is where the network finds a pattern in the training data that actually isn't a pattern in the real world. Shuffling the training data helps avoid this problem. As we're making only very tiny nudges to our network after each example, we'll typically want to run our shuffled up training examples multiple times through the network. Each run through the network is called an epoch. For simple problems, a network can get great results after 10 to 50 epochs. This is true with all the examples in this video. More complex problems will require more runs. For each epoch, it's a good idea to hold some of the shuffled training data back. Once we've completed the epoch, we can then see how well the network can perform on this sample of unseen data. This is called a validation set. In essence, this is a mini testing run at the end of each epoch. Now think of the data as being split into 3 unequal groups. The largest is the training data, used to nudge the weights and biases. The 2 smaller groups are the validation and test sets. Validation helps us understand the evolving performance of the network per epoch. The test data is used right at the end to give us the performance of the data in our trained network. You can choose what ratios to split the data into. The range 80-10-10, 70-20-10 is a useful starting point. So at the end of the epoch, we can record 4 numbers. 1, the cost function on the training data. 2, the accuracy number on the training data. That's to say, how many of the training examples were correctly classified. 3, the cost function of the network on the validation data. 4, the accuracy of the predictions in this validation set. All of this information can be displayed on a performance chart. Several points to note. Look at the red line here representing the cost function. You can see a very large drop in the first few epochs and a much slower lowering of the cost thereafter. You see a concomitant increase in the accuracy with both the training and validation data. Most important is the divergence between the training and the validation scores. The training cost is lower than the validation cost, and the training accuracy is higher than the validation accuracy. This shows the network overfitting. It is seeing patterns in the training data that aren't in the validation set. We want our network to be good at generalizing. If it picks up idiosyncratic patterns in our training set, it's of less use to us. We'll address some solutions to overfitting in this video series, but for now there are 2 very important takeaways. 1, the validation accuracy is a much more reliable estimate of network efficacy than training accuracy. 2, divergence between training and validation metrics is bad. We need to do everything we can to drive them closer. The performance chart makes use of our training and validation sets. But what of our test set? How can we make use of this and visualize our results? One of the best ways is to deploy a confusion matrix. At its simplest form, a confusion matrix provides a way of visualizing a binary outcome. A simple example would be the result of a diagnostic test. A patient either has a condition or they don't. A test will seek to predict whether the patient has this illness or not. There are 4 possible outcomes: a true positive, a true negative, a false positive, and a false negative. We can use the information in the confusion matrix to determine accuracy. This is the sum of the correct diagnoses divided by all diagnoses. The precision is the true positives divided by all positives, and the sensitivity, the true positives divided by the true positives and the false negatives. Our example is clearly more than a binary choice. We have 10 possible items and 10 possible choices. Rather than 2 squared or 4 outcomes, we have 10 squared or 100 outcomes. Here's the confusion matrix for our neural network after 50 epochs. There's a lot of useful information on this web page, so let's go ahead and interpret it. We've just dropped in a file that contains the results of our neural network from the previous video, a network with an input layer that takes thumbnail images, with 2 hidden layers, the first with 128 neurons and the second with 64, and finally an output layer of 10 neurons, 1 neuron to classify each of the 10 items of clothing. There's nothing special about this choice of parameters. We can easily add other layers and different amounts of neurons for each layer. Let's drag in the results of a larger network with 3 hidden layers of 256, 128 and 64 neurons respectively. You can see the confusion matrix alongside the performance chart. The first simple observation is that the test accuracy, 88.28%, is good, but less than the validation and training accuracy. Not by much, but there is some overfitting here. The test accuracy is easy to derive from the confusion matrix. Add up the 10 numbers on the leading diagonal and divide that by the sum of all of the 100 numbers in the matrix. The model predictions run on the horizontal axis in the first row along the screen. The actual garments run vertically in the first column. We can see that after trousers, this model is best at predicting bags. 969 are correctly classified. It's pretty good at predicting ankle boots with 952 true positives. It only incorrectly predicted an ankle boot 38 times. And then these were actually images of a sandal and a sneaker, perhaps understandable. The model is poorest at predicting shirts. While there were many more correct predictions than wrong ones, it did fall into the trap of thinking that something was a shirt when it was actually a t-shirt, pullover, or a coat. A prediction histogram shows us the results of the output layer. If we click on the cell representing the correct guesses of the shirt, the application will display these images below the confusion matrix. Alongside each thumbnail image, you can see the corresponding prediction histogram. This is a visualization of the output layer in our neural network. All of these images are correctly predicted as shirts. You can see that in many of these images, the network is very confident. In this network, neuron 7 has been trained to look for shirts. Its activation is very close to 1 for many of these samples. If we look at the top left image, we can see that the network is not quite as sure. Neuron 7 has an activation of 0.56, while neuron 1, looking for t-shirts, is not far behind with an activation of 0.43. Also, a non-zero activation for neuron 3, which looks for pullovers. We've set this up as a winner-takes-all output, which seems appropriate, but there's clearly the potential to use the ambiguity here for some applications. How certain is the network? Might some too close to call examples get fed onto a queue or another process? Might the labeling process encode some inherent ambiguity, by which I mean rather than classifying something as definitely a shirt, might we allow for some wiggle room? We're getting a little ahead of ourselves here, but we'll return to that specific point shortly. It's rewarding to look at where the network was correct, but it's much more illustrative to look at the examples where the network could improve. Take the 101 incorrect predictions where the model predicted a shirt, but the image was actually a coat. The color coding in the histogram helps the interpretation. The incorrect prediction is shown as a red bar. The actual garment is shown in green. All of the others are shown in blue. There are 3 very strong candidates for this second image, one of which included the correct label, coat, but shirt was slightly ahead. We can scroll down and see other examples of where the network made other incorrect assignments. If we look at where the network performs stronger, the ankle boot has 952 correct assignments, then we see a high degree of confidence on all of the images on the screen. Let's look at some examples where the network got it wrong. 24 examples where the network thought that the image was an ankle boot, when in actual fact the item was a sneaker. In most of these cases, there was a strong case for the correct answer. How might we look at this information to improve the network? To look at that, let's look at a different vision problem to solve: handwritten digits from 0 to 9. We can preview the digit set by making this selection. We'll retrain our 3-layer network on this data and display the confusion matrix, prediction histogram, and performance chart as before. We see much stronger performance on this simpler data set, but still some overfitting. That's very hard to eradicate. But don't believe the training accuracy of 99.5%. The more accurate measure is from the test set, kept separate from the train validate set during optimization. Again, we mostly have correct assignments here on our leading diagonal, but the insights really come from where the model gets it wrong. you can see that the model is overly fond of 8s. There are lots of elements in the 8 prediction column. Interestingly, there are much less incorrect predictions when the image really is an 8. The 8 row, for actual image, is much sparser than the 8 column, the predictions. We can see that there were 24 occasions where the model predicted an 8, but the image was actually a 3. The middle image in the top row looks like a 3 to me, but it's easy to see how it could be misclassified. If we scroll down, there are 2 very similar looking 3s that have almost identical activations in the final hidden layer. Again, for some applications, it might be insightful to utilize the full activation vector rather than take only the maximum value. There may be information content in the distribution of activations. This may also mean that we're less binary in our labeling. Take the instance of this 0 that the computer labels as a 6. Might our label here be 8 zeros, a 0.4 in the 6th neuron, and a 0.6 in the first? This would reflect the fact that there's ambiguity in the image. Of course, this would make labeling complex, but hopefully we can see how the network itself might help with this. We can revisit the misclassified data set and relabel it with floating point values rather than binary ones. This can then be used as part of the training set for further optimization. These are all exciting interpretations that will help us improve our network's performance. You can see the benefit of combining the performance chart, the confusion matrix, and the prediction histogram is greater than looking at each in isolation. The most important takeaway from this video is use it, interpret it, improve it. AI is great at spotting patterns and performing on data that it has not seen. Adaptation and updating parameters in response to new data is a key attribute of AI, but we can help it get better at getting better. Use, interpret, improve helps us get optimum performance from our AI projects. This is Richard Walker from Lucidate. Thanks for taking the time to watch this video. We've discussed a recursive approach to developing AI. Use it, interpret it, improve it. We've looked at some interpretation techniques, performance charts, confusion matrices, and prediction histograms. We've discussed overfitting and the information content in the output layer. Please join me in the next video where we take a big leap in sophistication and discuss convolutional neural networks. These networks help power some of the advanced AI at firms like Waymo, Uber, and Tesla for their driverless car programs. The next video will give you a solid foundation in how these networks are built and used.